we're going to start talking about floating point, which is how we deal with non-integers in a computer sense. So integer, of course, means a whole number, but now we'll be able to deal with the decimal point situation also. Okay, and to sort of motivate how we're going to do this, take a minute and think of some really big numbers that you can come up with, and also some really, really small numbers, right? So just come up with something, and then we'll kind of make a list of a couple of the things you guys come up with. All right, so anybody got a big number for me? That's not a number. Okay, infinity is not a number. Unless you're a math major, in which case then you can sort of treat it as if it's a number, but you have to have the special license for that. Okay, yeah, sorry. Nice try. 630 billion. Okay, that's pretty big. Anybody top that one? Okay, yeah, right. Yeah, we can play that game all day. 631 billion. It's right, sort of the opposite of the Price is Right kind of thing. Yeah? 10 times 10 to the 1,000 power? That's pretty big. Yeah? I'm kind of surprised nobody gave me this one, right? Avogadro's number from chemistry? Yeah? Okay. Um, you guys don't remember that? The number of atoms in a mole or molecules in a mole, right? Um, or while we're, okay, right. I mean, I did already say that infinity was off limits, right? So I guess that's right. Okay. Um, yeah. What about small numbers? That's not small. Um, likelihood that Liam has a date this weekend, maybe life expectancy of a beta theta pi hat. Okay. Um, but how about some other actual numbers that are small? Right. How about this one, which is the universal gravitational constant from physics? Okay. Um, all right. So, what I'd like to maybe key in on, other than the sort of joke numbers that we have here, are, oops, sorry, these guys here. All right. So, what's the sort of key for how we were able to express these really big and really small numbers? Yeah, with exponents. Okay. So, what is it called when we write them this way? Scientific notation. Okay. So, that's going to be kind of the key, is to think about the scientific notation. Okay. So, let me write them back down again. And I want to contrast. It's actually perfect that you gave me these. Well, we came up with these three. Um, what's different about the first two, the 6.022 times 10 to the 23rd and the 6.67 times 10 to the minus 11 versus the 10 times 10 to the 1,000. And you can kind of ignore that the two numbers on the left actually come from like science, and the third one's just sort of made up. But what do I notice? Yeah, the decimals, okay. And I could have written it as 10.0, okay, but really I should have written this one as 1.0 times 10 to the 1,001. Okay, so the convention with scientific notation is how many digits go before the decimal point? Precisely one. No more, no fewer. Okay, so would I ever write 60.22 times 10 to the 22nd? No, there's only one circumstance I would, which we'll deal with on Monday, which is when you do arithmetic with these things. But otherwise, our convention is that we write precisely one digit before the decimal point. And furthermore, would we ever put a zero before the decimal point? No, that's silly, because you could always just shift it down until something that's non-zero. Okay, so precisely one non-zero digit before the decimal point. Okay, and that point, or that observation, is going to be critical here in a few minutes. Okay, good. So let's think about, like, this is scientific notation in base 10. How would we do this sort of thing in binary? Well, how many digits do we have to work with in binary? Just two, 1 and 0. And if we say you can't put a 0 in front of the decimal point, what has to be in front of the decimal point? A 1 automatically, okay? And that means that we get basically 1 bit for free. Okay, so let me also, before we get into the binary part, let me make some terminology things. So we have here, let's take our 6.67. That is called the mantissa. And then, of course, we also have the exponent. And in this case, it's not present, but we have a sign, okay? And if I don't write a symbol, like a plus in front, then just the assumption is it is plus. And if it's negative, then I have to explicitly write the symbol, okay? But we have basically three pieces of information that we would need to communicate: the sign, if it's plus or minus; the mantissa, which is the stuff before the times 10 to the whatever; and the exponent. And if I tell you those three things, do I need to tell you the 10? Okay, so if I say, I want you to write a scientific notation number where the sign is positive, the mantissa is 6.67, and the exponent is minus 11, would you know how to write down the number? You'd write down 6.67 times 10 to the minus 11. How would you know that it's 10 to use for your base? What kind of arithmetic system do we use as just regular people? Base 10, right? So that part is assumed. Okay. So what we're going to switch all this to is how to do this in binary. So everything will get encoded in binary. There'll be a little bit of a weird wrinkle on the mantissa and the exponent, but it'll mostly work as sort of this idea of scientific notation. Okay. There's one other wrinkle that we have here. Okay. So let's compare, say, 6.67 and 6.022. All right, yeah, their exponents are different, right? Negative 23, or sorry, negative 11 versus 23. Not a huge difference between those. But then also, what's different about 6.022 versus 6.67? Yeah. Yeah, there's four digits in one and only three in the other. Okay. And in human arithmetic, you just write down as many or as few digits as you need, and it's no big deal. Okay. And, could you get away with 6.02 times 10 to the 23rd? Like, I mean, maybe Dr. Porter would take off points, but like, they're basically the same. Okay. But uh, on a computer, when we encode these things, we have to decide in advance how many bits are we going to use for all of these things. Okay, that would be like us deciding, okay, you get 6 digits for your mantissa and 2 for your exponent or whatever in base 10. Okay, we don't have that restriction in base 10. We use as many digits as needed, and that's that. Okay, but on a computer, we have to decide in advance how many bits or binary digits we're going to use for these different pieces. Okay, and so how many are we going to pick? Well, the sign is easy. Okay, how many bits do we need to encode plus versus minus? Well, there's only two options, right? One and zero, or sorry, positive and negative. So that only requires one bit. Yes. Okay. So so for the sign, we only need one bit. For the exponent, we're going to use 3 bits, and for the mantissa, we'll use 4 bits. Okay, and for a total of 8. Now, let me back up one quick second. Um, until the mid 1980s, there was not a completely standardized way of handling and storing floating point numbers. Some brands of computers did it slightly different than others, and like I said, it wasn't standardized um, until in 1985, I think it was. Uh, the IEEE, which is a sort of it's an organization that is a professional society for basically computer and electrical professionals, but then also it's a standards organization. So most of the standards, like how does Wi-Fi work, there's a standard for that, and it's an IEEE standard, and everybody makes their Wi-Fi equipment to adhere to that standard, and that means that your Apple laptops can talk to the Cisco router, can talk to the Dell laptop or whatever, right? So, um, okay, so this standard got ratified, and it basically specifies how to do floating point encoding. And it's been amended a few times, but basically it defines how to do 16, 32, and 64-bit floating point arithmetic. It doesn't define 8-bit arithmetic, okay? And there's a good reason, because nobody in their right mind would ever actually use 8-bit floating point. It's just way too imprecise. So why are we going to use 8-bit floating point? Because it's less crap to write down, and it'll actually make sort of the some of the challenges that you have to deal with floating point easier to see. Okay. Um, yeah. Okay. So is that all right? So 8 bits, even though you would never actually use this, the idea extends easily to 32 or 64 bits. And in fact, the scheme that we're going to use is basically, I took the IEEE standard for 32 bits and said, okay, if I were to pretend that this standard also applied to 8 bits, what would it say? And this is what it would say. Okay. All right. So the sign bit's easy. The exponent and the mantissa are going to require a little bit more work. Okay. So maybe the best way to sort of get our feet wet with this is, let's just pick a number. So I need a number, and I want it to have a decimal in it, right? So that we can encode it. So somebody pick me a number. Okay, 5.42. That's going to be a little bit too, well, let's pick something simpler. Like, how about 2.5 or 2.75? Let's do 2.75. That sounds more fun. All right, so 2.75 is my number. Okay, the first thing I need to do is write this in binary. Now, how do I write 2 in binary? 1, 0. Okay, that's easy. But what about the 0.75 part? Well, let's go back and think, well, what the heck does 0.75 mean? Where is the 7? What position is it in? It's in the tenths place, and the 5 is in the hundredths place, okay? So if I write down the place values, and this is what we've been doing for a couple days now, I would have that for the 2 part, right? A 1 in the 2's place and a 0 in the 1's place. But instead of the tenths and the hundredths place, what do I have this time? I had well, what is tenths? That's 1 over 10, right? Or equivalently 10 to the negative first. What's hundredths? That's 10 to the minus 2. Okay, so why do I have 2 to the minus 1 and 2 to the minus 2 in this case? What base are we working in? Well, base 2, right? Okay, so what is 2 to the minus 1 equal to? 0.5, 1/2. Okay, what about 2 to the minus 2? 0.25, right, or 1/4. Okay, all right, so if I've got 0.75, how do I want to think about that? Does 0.5 fit into 0.75? Yes, once, with how much left over? 0.25. Okay, great. Does 0.25 fit into 0.25? Yes, once, with nothing whatsoever left over. Okay, and for reasons that'll become clear in a moment, I'm going to go ahead and go one more position so that I have 5 bits written down. And I've put a real thick line there to indicate where the decimal point is. Okay, so I'm going to write this as 10.110. Okay, and then I'll write it times 2 to the 0. What is 2 to the 0, by the way? So I'm not actually changing anything if I just multiply by 1. Okay, but I'm writing it that way for a reason that'll become clear in a moment. Okay, we've got one other piece of terminology we need to get out of the way. What do I call that dot? Well, we call it a decimal point, right? But decimal is kind of a base 10 word, right? It has the very idea of 10 in it. So is that maybe the best term to use here if we're not working in base 10? Okay, we need some sort of word that's agnostic in terms of what base you're using. And the term that we use for that is the radix. Okay, from the Latin word which means root. Radish, by the way, same root, pun intended. Yeah, okay, so instead of the decimal point, we'll call it the radix because, again, we're not working in base 10. Okay, all right, is that cool? Okay, so does this fit our rule about scientific notation? Why not? It's not exactly one thing before the radix. This one has 2 things before the radix. Okay, so in the same way that I would write 6.02, not 60.22 for the Avogadro's number, I need to have this thing be kind of the correct form. Okay, so I'll write it as, how can I rewrite this? How about 1.1, or sorry, 0110 times 2 to the what? 1. Okay, how did you know it would needed to be 2 to the first? I mean, other than just using your head. Okay, so let me tell you guys a story. It's story time with Uncle Colin. Yeah. All right. How many of you guys have jobs that say aren't on campus? Okay. What's your job? Okay. Liam, did you raise your hand? You coach tennis. Okay. Well, it was when I was in college, for a couple of the years anyway, do you guys know what I did? I worked at Kohl's. Okay. So who's been to Kohl's to go shopping? Or how many of your moms have been to Kohl's to go shopping for you? Right. Okay. I used to be employee number 1245936. And I worked mostly customer service, but occasionally I do some other stuff. So, a couple of things about retail, well, particularly Kohl's, right? Did you find everything okay today, sir? Yeah. Is this going to be on your Kohl's charge today, sir? Yeah? Oh, you don't have a Kohl's charge. Well, if you apply for one today, I can save you 15% on your, right? So the whole credit card game of retail. But second, let's say that you want to buy this T-shirt, and this T-shirt sticker or tag says it's 19.99. How much are you actually going to end up paying for that T-shirt? Not 19.99. Okay, why? Well, okay, there's tax, yes, but if the sticker price on the T-shirt is 19.99, is that actually what you're going to get charged for it at a place like Kohl's? No, of course not. Does anybody ever pay full price on things at Kohl's or Penny's or whoever? I'm just picking on Kohl's since I used to work there, right? No, it's always on sale, right? And they play the game, right? Which is okay, let's say that the shirt is $39.99 is what's on the tag, but it's 50% off. Okay. So you'd pay $19.99. Would you rather have that one or a shirt that's 0% off but costs $19.99? Huh? Which one would you rather buy? The half off one, even though they're the exact same price when all's said and done, right? So they play into that psychology. Okay. So now you might wonder, what the hell does this have to do with floating point? Okay, I promise there's a punchline here. When they say it's 50% off or whatever, what do they mean? It's 50% off of what? The sticker original price, okay, which is either on the tag or the sticker. Okay. The other thing about retail, well, it's September, okay, which means the truck with all of the stuff for Christmas is starting to arrive because that's how things go in this country. Um, Christmas stuff is out way too soon, but what would happen the day after Christmas or any other major holiday? Yeah, all of the stuff from that holiday is majorly marked down. 75%, 90%, right? Because we want it the heck out the door so we can get that part of the store, the seasonal section, cleaned up and ready for the next holiday, right? In the case of Christmas, the next one is Valentine's. We want all the Christmas stuff gone. Okay, so I'm working a couple days after Christmas, and uh, the all the Christmas stuff, whatever of it remains, is now 90% off. Okay, pretty good deal, right? So a lady comes up to me and she says, "Is all the Christmas stuff 90% off?" "Yes, ma'am." "Could you please tell me how much this thing is?" She hands me something. I flip it over, find the original price on the sticker. It says $39.99, and I say $3.99, and I hand it back to her. Okay, great. 15 minutes later, she comes back with like a cartload of stuff. And she's like, "Can you tell me how much all of these things are?" And I'm like, "Sure." So I'm like $3.99, $2.99, $1.49, just burning through them. And she's like, just flabbergasted. She's like, "How are you doing this so fast? You must be really good at math." And I'm like, "Well, I do happen to be a math major, but that's not why I'm so fast at it." She's like, "Well, what do you mean?" I said, "Well, let me show you the trick, right? $39.99. What does 90% off mean? 10% of the price. So you see the decimal point? Move it one spot to the left. And her mind was blown. It was like that meme that's on, the animated thing of the guy in the black turtleneck, and there's like explosions coming out of his brain. He's like, you guys know what I'm talking about? Yeah. Okay. Her mind was just blown. Okay. So moving the decimal point one direction or the other is tantamount to either multiplying or dividing by 10, right? It's a base 10 system. All right, so in binary then, if I move the radix one position either direction, that's equivalent to either multiplying or dividing by 2, because we're in a base 2 system. But it's the exact same idea, right? Okay, so you see that the Cole story really did have a meaning here? Yeah? Okay. Okay, so several things. By changing it from this form, 10.110 times 2 to the 0, to the second form, I have made it conform to our rule that thou shalt have exactly one thing before the radix. Okay, so we buy that. Okay, the second thing that I've done, and you might wonder, why did I go ahead and put this 0 in this last position, is I want precisely 4 things after the radix, even if they're zeros. Okay, why 4 things? Well, in the encoding scheme, how many bits am I going to use for my exponent? I said 3. We'll deal with the exponent in a minute. How many things am I going to use for my mantissa? 4. And they are those 4 bits right there. Okay, the stuff that immediately follows the radix. And you say, but wait, Dr. McKinney, what about the one that's in front of the radix? Why is that not included? It can't be a 0. And how many choices for bits do we have? It's either a 1 or a 0, and it's not a 0, so do I need to specify it? No, because it has to be a 1, okay? So I get a bit for free here, and this is something that's unique to binary, because if, let's say I tried this in base 10. If I told you 0.022 times 10 to the 23rd, how would you know if it's 6.022 versus 3.022 versus 5.022? You would have no way of knowing without me telling you the digit, correct? But here, do I have to tell you that there's a 1 in front? No, because it can't be a 0, so it's got to be a 1. I don't even have to say it. Okay, does that make sense? Okay, so that is really, really nice. Okay, so we now know our mantissa bits, which I'll just denote as M for short. Okay, and now we need to deal with the exponent. This part's going to kind of drive you guys crazy, and I'm sorry, but c'est la vie. What's the exponent as I've written it right here? 1. Okay, add 3 to that, and you get 4, right? So the exponent is a 1. Add 3, and this 3 is called a bias. Okay, right now it may seem like I'm just pulling that out of thin air, and I kind of am. Okay, but there is a really good reason for it that we'll talk about on Monday. Okay, so why there ought to be a bias or an offset, A, and B, why is it 3? There are good reasons for those decisions. For right now, just do it. Okay. Okay, so if I had 1 and I add 3 to it, I now have 4. What is 4 in 3 bits? So how would I write this? It would be that, right? 4 in binary is 1, 0, 0. Okay? All right. Other than the adding 3 kind of coming out of left field, does that make sense? Right? So the fact that I added 3, I got 4, and 4 in binary is 1, 0, 0. Are we okay with that? Okay. Yeah, and I realize the adding 3 part seems completely arbitrary, but there's a good reason for it. Okay, so this is my exponent, and therefore my number is encoded as follows. The order that's specified in IEEE is this: sign, exponent, mantissa. What's our sign bit here? Well, is the number positive or negative? It's positive, and we choose 0 to correspond with those. The exponent we just said was this, and the mantissa is that. Okay, so that 8-bit pattern, that is our number. Okay? To encode, what did we do? 2.75, right? Okay. All right, good. And that ordering is the standard, right? So sign bit first, then exponent, then mantissa, however many bits you're using. Okay. All right, so question, preguntas, fragen on that. Okay, so let me go away from the notes for just a second, and let me come to this cool little website called Float Toy. If you Google for this, do it as 2 separate words. Most of the hits you're going to get involve pool noodles and other inflatables, but that's not what we want. We want this thing. Okay, so this website is sort of a little demonstration engine for the actual IEEE floating point standards, 16, 32, and 64-bit. And when I get off my lazy tookus, I'm going to add in the 8-bit thing to it, just for giggles. Okay, when you first load it, it has 4 demonstration numbers picked out. And notice, what are those demonstration numbers for all 3 of these schemes? They're pi, right? And so all 3 of these are the maximum degree of precision that you can encode pi in 16, 32-bit, or 64-bit standards. Okay. Now, the 32-bit, does that look pretty good in terms of the number of digits? Yeah, okay. And the 64-bit, that looks really good. This does beg the question, by the way. Pi is certainly an important number in the universe. If I were NASA and I wanted to compute trajectories to get a space probe to, I don't know, Pluto, how precise of an arithmetic system should I use? I better be pretty precise, right? Because I don't want to, miss Pluto or crash into it. They use 64-bit double precision. That's enough for NASA to get all the way to Pluto. And in fact, the rounding error there on pi, right, because pi keeps going, so there's some decimal, or there's digits that have been chopped off. That's precise enough to be like off by an inch or so by the time you get out to Pluto's orbit. Could we all agree that's probably close enough? Yeah, okay. So 64-bit is really damn precise. But let's go down to 16-bit. 3.141 is the best you can do. Is that pretty precise? I mean, now it's kind of a matter of argument, right? What did you guys use for pi, or your approximation for pi when you were in school? Usually 3.14 was sufficient, right? It's not like you were building rockets or anything. 3.141, all right, it's close enough, but not really all that great. Okay, let's compute the best we can get for pi in our 8-bit system. And it's going to kind of shock you. Any guesses as to what it's going to come out to be? 3? That's a good guess. It's actually a little better than that, but still pretty terrible. And that's sort of actually kind of apropos because did you guys, well, how many of you are from here in Indiana, right? Did you guys learn about the Indiana Pi Bill when you were in school? No? So about 100 years ago, there was a bill before the state assembly that, amongst other things, would have the effect of legislating the value of pi in Indiana to be 3. Now, there's a long story behind it, and it didn't actually say that about pi, but that would have been one of the effects of the bill. And this was here in Indiana, right? I mean, that's the kind of crap I expect out of Alabama or Arkansas. Yeah. Where your family tree is a recycle symbol. No. Yeah. Both sides of my family are from Arkansas, so I feel like I have license to make that joke. Okay, so let's figure out what pi is in our 8-bit system. And the best we're going to end up able to do is 3.125. So not quite as bad as just 3, but not quite as good as 3.14, blah, blah, blah. Okay. So, all right, so let's do, let's get our place value stuff set up. Okay. So, pi is 3.14, blah, 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 right? So do you guys accept that I definitely need a 1 in the 2's place and the 1's place? That gets us our 3. Okay. So what we have remaining to deal with is the 0.1415, blah, blah, blah. Okay. The next position is the 2 to the minus first place. What is that 2 to the minus first as a decimal? 0.5. Does 0.5 fit into 0.141, blah, blah, blah? No, does not. What's the next position as a decimal? 0.25. Does that fit into 0.14, blah, blah, blah? No. What's the next position? The 2 to the minus third is 0.125, okay, 1/8. Does 0.125 fit into 0.141? Yes. Once with some leftover, okay? But can I even consider the leftovers? Why not? Yeah, I've run out of bits, basically. Okay, so how many bits do I get to use here? I get to use at most 5 because the first one is the thing that needs to go before the radix, and the other 4 are my mantissa. But how many mantissa bits did I say we get? 4, not more than that. So even though there's more, like we should keep going with this, like mathematically we should keep going, we can't because we've run out of bits. Okay, so the number is right this instant 11.001 times 2 to the 0. Okay, and then we say, wait a minute, does this conform to our rule? No, so what I need to do, shift the radix, oops, and write it like so. Okay, so see, I did the Coles trick, right? Okay, so what does that make my mantissa? Yes, right? It's the stuff after the radix. Okay, and then what about the exponent? That one's actually the same as it was last time by coincidence. Okay, the exponent appears to be a 1. I add 3 because just shut up and do it. And then what is 4 in binary? 1, 0, 0. Okay, and finally my sign, well, pi is positive, so I'll make my sign bit a 0. Okay, Gucci? All right, so the encoding would be sign bit 0, exponent 1, 0, 0, mantissa 1, 0, 0, 1. Okay, and this is 3.125 as a decimal number. That's the best we can get with pi. Okay? All right, so question, preguntas, and or fragens. And I guess you football guys have to jet. I'm going to have to go yell at somebody because the dean's excuse they gave us was for afternoon classes. And this is not an afternoon class. So I'll have a chat with somebody. Okay, so for those of you guys who are about to split, what we'll finish with today is how to decode. So how to do this process in reverse. So just catch the last 10 minutes of the video. Okay? Question? Yes. No. How do you know where the decimal is? You know the scheme, right? So okay, yeah, so good point. I'm not actually writing the decimal in terms of how I would store the data on the machine, okay? So how does the machine know where it is? Well, the machine is constructed knowing that standard, okay? And furthermore, I would have to specify, like if I'm programming, which standard am I using? Am I using a 32-bit standard or a 64-bit standard? And then the hardware would have to support that, okay? Yeah, because the whole problem, right, is that, like, what is a decimal point? How does a computer store that information? It's almost a meaningless question, because what can the computer store? Ones and zeros. That's it. Okay. Um, yeah. So the radix, you just have to understand the system, and if this is sort of the complicated part, right? Because let's say that Apple back in the 70s did it one way, but Microsoft did it another way. Well, how would you be able to communicate between those two machines? You'd have to know, oh, this information came from an Apple, so it's in this system, and convert it or something. Okay. Um, yeah. But it's always in that order: sign, exponent, mantissa. And the sign is only 1 bit. That's all you need. Exponent 3, mantissa 4 for the 8-bit scheme, yes. So for the exponent, why do we have 3? Why don't you just do the 2 zeros? Yes, okay. So there's a good reason for that, and we'll talk more about this on Monday. So why do we add anything? And also then, therefore, why do we add 3? Okay. Um, the reason is it makes it easier when you look at an exponent of two different numbers to automatically know who has the bigger exponent and therefore which one has the smaller exponent. Why we need to be able to do that is if we, like, let's say that I have two floating point numbers and I want to add them together. Okay, then it's where it's critical to know that. Okay, and so choosing that scheme for the exponent may seem kind of bass-ackwards, but it actually makes that question to determine exponent size real fast. Okay, so that's why we do it. Okay, now why 3? Because it makes the arithmetic work out nice, and maybe that will become, like I said, a little bit more clear on Monday. And while we're on the subject of that, a quick sort of piece of terminology. This final number where we have exactly 1 digit before the radix, or 1 bit in this case, okay, things that conform to our rule, we will call those numbers normalized. And any number that's written in a non-normal form, we will call denormalized. Okay. When we do arithmetic, what we'll have to do is deliberately denormalize one of the two numbers, and we'll choose the one that has the smaller exponent for reasons of precision. So like I said, we'll get there on Monday. But for right this instant, the last thing we need to do is, well, here we picked a number, base 10 number, and then figured out how to encode it. What's the opposite process going to be? Yeah, if I give you a binary representation of something, how do you figure out what it's equal to or what it represents? Okay, so the decoding side. Okay, so do you guys see the distinction here? Yeah? All right, so let's make up a binary number. I'm going to switch to a clean sheet. Is that okay? Any objection? All right. So let's make up a binary number. How about we do 1, 1, 0, 1, 0, 0, 1, 0. And I'm just making that up. And we'll say this represents question mark. Okay, so the first step, and this maybe gets to your question from a minute ago, is how do you know where the decimal point is, or the radix? Well, we need to carve this 8 bits up into its 3 pieces. What is the sign bit? 1. And that tells us immediately that the number is a negative, whatever it is. Okay. What are the exponent bits? 1, 0, 1. And what are the mantissa bits? 0, 0, 1, 0. Okay, so I'm going to write 1 point mantissa times 2 to the exponent, but I have to take away 3 from the exponent because When I encoded these things, I have to add 3. So I've got to do the opposite of that process. So what does 101 look like in binary? Looks like 5, right? And if I take 3 away from that, what do I have? Okay, 5 minus 3 is 2 last time I checked. Okay, multiplying by 2 squared is how many shifts of the radix? 2. And which direction? To the right. Okay, because remember, going to the right is like multiplying by 10, and going to the left is like dividing, or sorry, multiplying by 2, and going to the left is like dividing by 2. Same thing at the as at Coles. Okay. Okay, so now we're almost done. Do I really need to have the times 2 to the 0 at this point? Because what is 2 to the 0? 1. Okay, so 100.10. What is all this? The 1 is in which place? Ah, the 4's, right? Because this is in binary, right? Still. So this is in which place? 1's place, 2's place, 4's place. So I've got 4.5 because it's in the halves place. Okay. And so what's our number? It's negative 4.5. Okay. Negative because the sign bit was a 1. And then the 4.5 part we just figured out. Okay. All right. So what's the really annoyingest part of this is that dang bias. Okay. That subtracting 3 or adding 3 bit. Like I said, there's really a good reason for it. But for right this instant, just take it on faith. Okay. And we add the 3 when we are encoding, and therefore we need to subtract the 3 when we're decoding. Don't get them backwards because otherwise it'll get all screwed up. Okay. Um, okay. So is that okay? Yeah. Um, yeah. Okay. So sign bit, exponent, mantissa, it always is in that order: 1, 3, 4 for the number of bits. And that number of bits, it depends on which scheme you're using. So for example, if I go back to float toy, the color coding here is the sign bit is always in front, and that he's coded in blue. The exponent bits are in green, and the mantissa bits are in red. And you'll notice that most of the bits are allocated to the mantissa. Okay. And so on our scheme, we had 3 for the exponent, 4 for the mantissa. For these other ones, it's like for, let's say, the 32-bit, it's 8 bits for the exponent, 1 for the sign, and that leaves 23 left over for the mantissa, right? So most of them are going to the mantissa, and that actually is a good thing. Okay. Because it allows you to have more precision. Okay. Yeah. Okay. So, any other questions, Preguntas and/or Fragens? No. This will take a little bit of practice. This is why you have the homeworks or whatever on Canvas. Okay. And we'll continue, I guess, with this on Monday. So, have a fantastic weekend, and try not to lose your hat.